So I want to welcome everyone to another Science Outreach Athabasca event, and thank you all for joining us. I wanted to thank Yan-yin for doing this talk for Science Outreach Athabasca, and please feel free to post any questions in the online chat or ask questions in person at the end, which we will go through at the end of the presentation. Please let us know in the chat if there's more than one person watching this presentation on your computer so that we can keep track of it for our records and maybe where you're joining us from. This talk will be recorded and posted onto our Science Outreach website and YouTube channel at a later date. Please watch our website for any other upcoming talks. And our next talk is on February 22nd, bioconversion of methane to biodegradable plastic with Marina Lasic. I will now turn things over to Roland, who is one of our Science Outreach volunteers, and he will be introducing our speaker and moderating this talk. Thank you.
Yeah, thank you, Linda. Good evening, folks. Thanks for joining us. I'm Roland Troy, and I have the pleasure to introduce tonight's speaker. Yan-yin Wang is currently in the Sullivan Lab of the University of Alberta. Yan-yin grew up in Guangzhou in China, and he completed a BSc from Sun Yat-sen University in Guangzhou and an MSc from the Institute of Vertebrate Paleontology and Paleoanthropology from at the Chinese Academy of Science in Beijing. He is currently pursuing a PhD on respiration in dinosaurs, and he's doing that at the lab of Dr. Corwin Sullivan, University of Alberta. Yan-yin has taken part in paleontological fieldworks, both in China and in Canada. In the past 2 years, he joined fieldwork in Grand Prairie, for an example, as a part of the Boreal Alberta Dinosaur Project, led by his supervisor, Dr. Sullivan. So I would like to welcome Yan-yin for tonight's talk. And just to emphasize again, we'll have questions at the end. If you have written questions, you can do that at any time in the chat box, and we will try to cover all your questions after the talk. Without much ado, welcome Yan-yin, and thank you for doing this talk, and please go ahead.
Thank you, Dr. Hewitt, for the kind introduction, and thank you everybody for joining us tonight for our little talk on dinosaur stuff. So my topic is going to cover the ribcage portion of the dinosaur. So it's a little bit unconventional compared to some of the classic paleontological talks, and we will tie in a little bit more on the breathings and possible the mechanical implication we can see using modeling techniques. So let's get started. So first we need to talk a little bit about what is archosaurs. So it's not the same as dinosaur. We typically taxonomists would define archosaurs as a group of vertebrate animals that include the common ancestor of crocodilians and birds and all their descendants. So we can use this little diagram here as a visual example. So we have crocodilians on the left and we have birds on the right, as exemplified by this lovely osprey over here. So the archosaur can trace all the way back when the two groups meet. And the group archosaur would contain crocodilians and birds, of course, but also all the non-avian dinosaurs. So the tyrannosaurids, the horned dinosaurs, duck-billed dinosaurs, or the dome-head dinosaurs, all those cool and fancy fossil dinosaurs we can see in Jurassic Parks or Jurassic Worlds. And this group of animals first appeared back in the Triassic era, the Triassic time, and they kind of peak during the entire Mesozoic era. In the case of Canada, we have found many non-avian dinosaurs, particularly in the Cretaceous period. But then after the Cretaceous period, as many of us would know, the extraterrestrial impact has caused a drop in the diversity. So basically all the non-avian dinosaurs went extinct. And all we left today would be still a decent number of birds and about 23 species of crocodilians, but nothing compared to the level of diversity we can see back in the Mesozoics. Another thing we need to introduce is the uncinates. So it's a little hook and tab structures that we can find on some of the dorsal ribs. So those are the ribs that that made up of the rib cage, basically. And on the back of these ribs, we can find either a cartilaginous tab. So you can see on this crocodilian example, the cartilage is a little bit rough on the surface compared to the bone. It could be cartilaginous and tab-like, or it could also be ossified. So that means it becomes bone and looks a little bit more like a hook. So this represents, this actually gave the name of Uncinates. So the first anatomists back in maybe in 1600s, when they first find these structures, because they think find these structures in birds, because they think this structure represents a hook, and that's why they use the Latin word uncinate to name it. Uncinate just means hooks. And this is a 3D models we made from an ostrich here at the University of Alberta to show you the morphology of the uncinate in 3D. We can see this is really thin structures and not too prominent compared to the majority of the rib. Now, okay, all good with all these processes and but what do they really do in terms of breathings? So far there are many hypotheses for the functions of uncinates, but there are one specific hypothesis, meaning breathing has received experimental support. So in these studies, Jonathan Cott and his colleagues, they found a Canada geese, and they sedate the Canada geese. So it's kind of putting us in the operation room. They give sedation to the geese so that they won't feel any pain when they operate on the animals. And they locate the muscle associated with the uncinates. In this studies specifically is the number 2 muscle here, or the appendicocostalis, as we call them. And Cott et al. Put little metallic plates inside of those muscles, so that when this muscle is activated, we can detect this electric signal coming out from the nervous systems, and we can see the result of this experiment is coming out in the form of this peak or in some columns, if you would, or some kind of waveform if you modified it a little bit more. And by looking at this pattern and then monitor the time from the Canada geese breathe in and breathe out, what Jonathan Cott and his colleague did is correlating the muscle activity and the breathing cycles. So when these two are put together, they find out that the appendicle costalis, in this case, the muscle acts as inspiratory muscles, meaning when this muscle is activated, it causes the Canada geese to breathe in or inhale. So that's really nice physiological experiment to show that uncinate is related to breathing. And then in 2019, they expand their study a little bit, so which is nice. Now they worked on crocodilians with the same focus on uncinate, even though the muscles are different. And this time they focus on a muscle called the iliocostalis, which is a really large muscle coming out all the way from the pelvic or the hip of the crocodilian all the way to the shoulder girdle. And they will attach, the muscle is attached to the uncinates, of course. And by doing the same experiment, catching the muscle activity and correlate it with the breathing cycle, and again, they determined that the iliocostalis is, there's a typo here. It's actually an exhale muscle. So when when iliocostalis is activated, it will drive the crocodilians to exhale. So now we have two examples, one from birds, one from crocodilians. Both suggest that uncinate has something to do with breathing, either helping the muscles to inhale or exhale. And we can draw two competing hypotheses just from these two examples. Now, the first hypothesis would be saying, okay, because this living representative would both have uncinates as part of the breathing mechanisms, then it's most likely that all their extinct members, namely all the non-avian dinosaurs, would have the same adaptations. So they would have uncinates in some forms and shapes, and these uncinates would also be included in the breathing activities. And this kind of interpretation is what biologists would call a homologous statement. So that just means the same biological makeup. In this case, the uncinates are inherit from an ancestral archosaurs, and they remain in the same way in all their descendants. And we happen to see this in crocodilians and birds. An example for homology, this might be a little bit childish. It would be, say, the color of myself and my hypothetical brother are both black because we are both from China. And the color black is inherited from our parents. And even if my brother dye his hair into some colorful yellow, it will come back as black. The information we inherit from our parents remain the same. Now, this is the homologous hypothesis, and the competing hypothesis is what we call the homoplasic hypothesis. So in this hypothesis, the crocodilian uncinates and the bird uncinates, they are just happen to develop on their own. There's no correlation with parenthood or whatsoever. They happen to have the same functional needs, in this case, breathing, and then natural selection pushed crocodilians and birds to develop a structure called uncinates separately. Another silly examples in this case would be both myself and my hypothetical brother would make a pumpkin head for Halloween. So even if the pumpkin head looks mostly identical, they are not coming from our biological parents. So that's just something we want to clarify a little bit. So with these two hypotheses, the most intuitive way to explore this question would be looking into the fossil record. And I'm going to show you guys a couple examples that already have been published or already have been found in non-avian dinosaurs. So let's first look at what we call the Panaraptorans. So this is a group of theropods that kind of related to the famous Tyrannosaurs, but also it contains all the modern birds. So all the modern birds are sparrows, Canada geese. They all fall into this para-avi group. And then the oviraptorosaur is one example would be over here, the Apatoraptor it's a very interesting group of dinosaurs. Unfortunately, we don't have the time to really delve into it. But what we know from the record of Panaraptoran is that they have ossified uncinates, just like the structure that the red arrows are pointing at. And these uncinates are almost exactly the same as we can see in modern birds, although you can argue they're a little bit longer or narrower structures. But we can say the uncinates are there. The bird-like uncinates are there. And then there are some other studies on ornithischians, so a group that contains horned dinosaurs, the dome-head dinosaurs, and the duck-bill dinosaurs, basically. And what the scholars have found is they found this kind of broad, kind of calcified plate-like structures coming out between the ribs. And in the literature, these structures are typically called the intercostal plate. So intercostal just meaning this structure is located between two ribs. And that's what taxonomists or anatomists would call a costal region. And then the intercostal just meaning it's coming out between two ribs. And morphologically, I would propose these intercostal plates look remarkably similar to what we just saw in crocodilians. And in crocodilians in particular, really old individuals, cartilage can also calcify, and then they could be potentially preserved in the fossil record in the same way as we see from these ornithischians. And of course, we also have one more example from crocodiliforms, basically some of the ancestral crocodiles. And unlike the modern crocodiles, unlike the modern crocodilians, these crocodiliforms, in this case, the notosuchians, they're actually more terrestrial, meaning they don't really swim as much as the modern crocodilians. Then the interesting thing for us today is, of course, they also have this prong-like uncinates. Looks a little bit more like the hook uncinates in birds than the plate uncinates in crocodilians. But we cannot fully rule out the possibility that only part of the uncinate is preserved in this individual. But we can confidently say, okay, there is an uncinate in notosuchians. Good. If we look at all these examples, one thing probably comes to mind is that all these fossils are really, really well preserved. That means we don't have too many fossils in the fossil record as nicely preserved as this. So it kind of limits our ability to observe and document the uncinates or document the presence of uncinates directly. So this got my supervisor and myself thinking, maybe we can use something indirect, maybe some morphology on the rib can inform us that an uncinate was there, but not preserved. And this got us to look at the surface feature on the rib where the uncinate is attached. And that comes from the title, the attachment site of the uncinates. So to do this, we go into the modern collection where we have many birds and crocodilians, and with permissions, we move the uncinate from the corresponding ribs. And what we find is at the contact between ribs and uncinate, there is this rugose, a little bit concave area that kind of looks really different from the rest of the rib. So in this case, we can see in the rear, it kind of expands a little bit and the surface is highly texturized. And in the case of crocodilians, it's a somewhat irregular concavity with two really rough attachment sites. So we were thinking, maybe we can use this as a proxy to tell us whether in the fossil dinosaurs, whether there is a uncinate or not. But to prove this method to be valid, we need to see whether we can find something, some fossil crocodilians that within the same genera or within the same species as the modern one, so that we kind of validate our approach. And lucky enough, we managed to find two dorsal ribs from a fossil crocodilians housed at the American Museum of Natural History, as we can see right here. So this lovely little rib is from the Miocene of Wyoming, actually. And if we look at just the uncinate attachment, or we call them the uncinate scar, it morphologically or superficially, it looks almost identical to what we saw in the modern archosaurs. So that's perfect. So this is a valid approach to identify whether an uncinate is present or not in fossil dinosaurs, even if we don't have the uncinates themselves preserved. And in the following couple slices, I'm going to show you some variations we actually happen to capture during our collection visits. So this is an example. These are 3 examples of uncinate scars in Tyrannosaurids. So you can see the really texturized surface is the same as modern birds, and the shape is a little bit more suboval, as we call them. But unlike modern birds and crocodilians, Tyrannosaurus seems to have this proximal ridge, or as we call them. We can also see this on the 3D models over here. So it's kind of like a protrusion of something pointing out away from the rib itself, forming a shelf for the uncinate scar. So this is kind of interesting feature that we only see in Tyrannosaurid, really, in our studies. There may be something more to be discovered about the uncinate scars. And another variant or another variation we can see is actually from the ceratopsians or the horned dinosaurs. And in this case, the uncinate scar is really, really tiny little bit. It's almost the size of one single toothpick, and it's really narrow and long. So like this would be the outline of the uncinate scar. And we can still see it is concave. It still has the rugose textures. And in some case, in this particular individual, we are able to see what we identify as calcified tissues covering up on top of the uncinate scar. So that's kind of interesting variations along with the Tyrannosaurid. And there's one more example I want to show you is the ankylosaurs or the armored dinosaurs, those with armor plates and then a club on the tail, if you recall. In these guys, we can find this uncinate scar at a similar place with the similar texture as birds, but they are more developed in the sense that the width is more than that of a bird. And that this would indicate that the uncinate in ankylosaurs might actually be quite developed and large. And there have been some studies suggesting that uncinate or intercostal plates are present in ankylosaurs, particularly two species from Mongolia. Okay, so now all these surface features and identifications are nice, but if we are being more judgmental or critical, then we might need to think about what if it is not an attachment for uncinates? What could they also be? And then we thought about a couple of alternate interpretations, and then we are able to rule out two interpretations as highly implausible. So one of them would be muscle attachment onto the rib. So we know the rib cage is really complex with multiple layers of muscles attached to individual ribs. So maybe some of the muscles just happen to leave a scar on that specific spot. A typical muscle scar we can see it would be from a femur of a non-avian dinosaur here. So it does have that rugose texture on the surface, even though it may not be concave as we saw on the uncinate scars. And to really explore this, we did some dissections of modern birds and crocodilians. I'm not going to show you any of the gross photos, so don't worry. But what we found out is all these muscles in vicinity of the ribs, they are all kind of like a flat sheets of muscles, and they don't really leave robust scarring on the back of the ribs or on anywhere of the rib really. So that kind of ruled out the possibility of muscle attachment site. So another interesting possibility for those ceratopsian uncinates, because they are, as I was saying, they are just the size of toothpick. So maybe they're not really uncinate scar. Maybe they are bite marks left by some carnivorous predators. So we look up a few examples of classic bite marks left on bones. We can see they are all pointed out by all those arrows, and they represent different directions where the predators beat down on the bone, basically. And compare our uncinate scar and the classic bite marks, what we found was bite marks typically have more than one non-bone, as well, dinosaurs have more than one teeth typically. And our uncinate scar is only present once per rib. So that's kind of reduced the possibility of our horned dinosaur uncinate scar to be a bite marks. And another thing is our uncinate scar, this long axis of the uncinate scar is parallel to the long axis of the ribs. And in classic bite marks, such alignment between the bite mark and the long axis of the bone is either really rare or something that I have never seen. So if what we saw in horned dinosaurs are truly bite marks, I would argue this predator just have impeccable table manners, who would just aim at the bone really meticulously before it chew down onto the meat. I find this scenario highly unlikely, and so we can rule out this two possibility and really maintain our first interpretation that all these uncinate scars we saw in fossil old dinosaurs are truly representative of the uncinate attachment site. And all these individual dinosaurs we saw with uncinate scar should have an uncinate. That said, those are all surface features, all nice and well. But we might thinking maybe we could look into the microscopic level so that we can get additional support for our identifications. To do that, we need to rely on a technique or called histology. So basically, histology is the study of tissues and how they are composite at certain areas. For our purpose, we are interested at the contact between uncinate and rib. So we need to look at the tissue, like the cells or how the bones are looking at the junction between uncinates and ribs. And to do that, we need to make really, really thin slide across the rib and uncinate, as we can see here, represented by the yellow and green line. The thickness of the cut really depends on the techniques you are using. For these two individual slide particular, they are about 5 microns thick, so that's even thinner than our hair, if I recall correctly. And then we put on staining agents, so basically color for cells, and then they soak up those color, and we can see more details under the microscope. And let's look at the modern crocodilian birds first, and then we will go on to the dinosaur stuff. Okay. And so this would be two zoom in area of the turkey section we made. So the orientation is a little bit tricky. I would say the top half here would represent the direction of the uncinate, and then the bottom half area here will represent the position of the rib. So we are looking at the rib kind of horizontally, or just or transversely, if you are comfortable with this terminology. So this area here, as I pointed out, represents the rib, or more like the cortex of rib, or the outer layer of the rib, and this would be the connective tissue that binds the rib with the uncinate. Because we are more interested in what we can see in the rib, so we can ignore the top half here, and by looking only at the rib side, what we can see is there's a higher number of what we call the sharpest fibers. So they are basically steel bars we put in cement, or wires we put in clothing to form a mesh of support, so to speak. So there's one group of sharpest fibers going in this way. They're kind of bright and red in color, and then there's another group of sharpest fiber going in this way, and they're a little bit darker. So this kind of organization and the number of sharpest fiber is interesting and not seen in area away from the uncinate scar. And another feature we can find is there's huge holes going on, or you can also see it from here. So these are modified osteon. So osteon is the basic unit that made up bones. So if we cut open the bone, an individual unit would be an osteon. It's the same idea as, say, cut down all the matters, and then the basic unit that makes up the material would be atoms. And compared to the osteons away from the uncinate scar, the osteon at the uncinate scar is modified into a weird shape, and they have really large central canals or just large holes for our purpose here. Okay, so let's look at crocodilians and see if we can have a consistent picture between the two. Unfortunately, we don't really see those weird looking large secondary osteon with large central canal, but we do see the same pattern of the Sharpish fibers, like those hair-like structures kind of light up in this direction, and the black color hairy structures going in this direction. So at least we can say the high number of Sharpish fibers could be indicative of an uncinate. Here is just a region that's away from the uncinate scar for our comparative purpose. So we can see there are some Sharpish fibers going on, but there's not as many not as many as we can find at the uncinate scar, and they are not organized in the same way. So this is probably a good indicator. So now let's look at the cool dinosaur stuff. So we cut, again, like what we did with the crocodilians and birds, we cut open a tyrannosauric rib and make it really small. And then what we see is there's, again, this really large, irregular shaped central canal of the secondary osteons. There's one particular here is like about this big. There are something filled in the hole. Those are damage done to the fossils after the animals is dead. They are more or less representing an artifacts rather than natural features. So there is one thing that's consistent between Tyrannosaurus and birds, and here is a comparison between the really large central canals with the normal size central canals. And another feature we can see is around this region over here. If we enlarge this, and we will see those hairy-like Sharpish fibers are there. And they are kind of organized in a similar way as in birds, but they are not as prominent. So maybe Tyrannosaurids are doing something slightly different, given that the uncinate scar themselves are a little bit more unique in Tyrannosaurids. And we did the same thing for ornithischians, like represented by this centrosaur horned dinosaur here and this duck-billed dinosaur here. And again, we can find distinct patterns of organizations of the Sharpish fibers going between the rib and the uncinate scar. So even though we don't have an exact same pattern across the board, what we can say is whatever structures are laying within this uncinate scar, in our opinion, that would be an uncinate, the individual is trying their best to hold on to these structures. Because like in my really bad metaphor with steel bar and cement, the Sharpish fiber act as an agent to hold on to stuff or anchoring something from the outside onto the bone. So this good indicator that what we saw is that we can use to identify uncinates in fossil dinosaurs, even if they're not preserved. So, but still, we can still argue that we just saw all this from individual non-avian dinosaurs, but yeah, let's count them up. It's less than 100, but we have thousands of dinosaur species. How can we reasonably make an inference that whether the really ancestral archosaurs would have uncinates or not? And we do that by doing an analysis called the ancestral state reconstructions, which is kind of figuratively represented by this figure over here. So we basically put our observations on the right-hand side, and then use an algorithm to say, let's guess whether these key points would have cartilaginous uncinates or ossified uncinate or not at all. And we do it with a couple methods, like the most classic would be, say, parsimony or maximum likelihood and Bayesian. So we did all three methods, and then what we find out is it's most likely the cartilaginous uncinates would be the condition at the point of Archosaurias. So basically, it's the same as saying the presence of cartilaginous uncinates is likely a feature shared by all the archosaurs. And what we see in individuals we see without uncinate would be a secondary loss, and then they simply don't inherit that feature from the ancestral archosaurs. But most dinosaurs should have an uncinate. So now this is interesting because we saw from the Jonathan Cott's study on Canada geese and the American alligator that uncinate is related to breathing. So perhaps the same function is likely present in all these non-avian dinosaurs. So this is kind of cool. Because dinosaurs become such a dominant group of animals in the Mesozoic. Maybe there's something going on. Maybe the advantage of breathing assisted by uncinate has something to do with their biological success in the Mesozoic era. Up to this point is all nice and well. Yes, we infer that there is uncinates in all these dinosaurs, but how exactly do the uncinates help with breathings, right? Even with experiments done by Jonathan Cott and his colleagues, they only suggest the muscles is activated, but there's nothing said to how the muscles help the individual breathe with uncinates or without uncinates. And studies like this has been done since Zimmer in 1935. And there was more studies on general breathing topics even before Zimmer, but Zimmer is the first one focused on uncinates in birds. And then there's also follow-up study by Peter Tickles in 2007. All these studies are nice and really, really decent work. However, they are all two-dimensional in scope. So they kind of take a screenshot and really simplify the motion of the ribs into forward and backward. So like when you breathe in, the rib moved forward, and when you exhale, the ribs move backward. However, if we try to move our upper arms, like our humerus, we can feel the rotations are moving in 3 dimensions. So there is a little bit limitation going on in their studies, and luckily with our powerful computers today, we can do some decent simulations and really understanding the function of uncinates in 3D. So what we do with our software is we put all the bones, or we make 3D models of individual bones in Maya, and then put them in Maya. It's a 3D software help us to manipulate and visualize movement. And within Maya, we kind of design motions. So we design motions like this as representing a resting condition. And then we design the next motion where the sternum is not moving, representing an individual is resting with the chest touching the ground. And then the last one is just try to breathe in as hard as possible. And then from Maya, we put in all the information into a software called SIM, or the software for interactive musculoskeletal modeling, if you want to be more geeky. And inside SIM, we can reconstruct the muscles as individual lines or muscle vectors, if you want to be fancier. So individual line would represent one muscle. And then we can translate all these motions designed in Maya into SIM, either with design acceleration or without an acceleration. So in my opinion, something with an acceleration seems more natural, or just intuitively makes more sense. And we are going to use this line over here as an example, because I have 122 muscles. It might take a bit longer for us to discuss. So let's just use one as an example and see what we can do with this modeling technique. So what we will get is this kind of called the moment arm plot. So moment arms, for those who are not familiar with mechanics, is the advantages of rotating stuffs, basically. An example would be, say, if we try to eat ice cream and we hold on to the spoon at a very low position, it takes a little bit more effort to scoop out the ice cream. And if we want to have an easier time, we will hold on to the far end of the spoon, right? So the length of the spoon would become the mechanical advantages known as the moment arm. The same goes for the muscles. And we can see what we are seeing here is the moment arm during that entire breathing cycles. It's like here, starting from most exhale to breathe in, and to max inhale, and then back to max exhale. And this is what we are seeing on the graph. And we can ignore the exact value and stuff. Those are not the key information we want to talk about today, but we can see from the sign and the rotation direction that we can say the muscle associated with uncinates, namely the appendicocostalis, the action of this muscle can only cause the rib to rotate towards inhalation. So it only functions as a breathing muscle, whether the muscle is activated or not. So our study would kind of confirm what Jonathan Cott and his colleague has found in their experiment. But what we can also see is, what we can also do is compare the muscle of the appendicocostalis to the muscle next to it. So that would be comparing a muscle with uncinate attachment to a muscle without uncinate attachment. By doing that, we can say, this kind of comparison is almost like doing a hypothetical experiment where an individual without uncinate, how would their muscles perform differently? And so we look at a muscle just next to it, next to the appendicocostalis. It connects between two ribs, roughly around here. but on the inside, it does not contact the uncinate itself. And we can see the pattern is a little bit different. So the moment arm is much smaller in magnitude, and it's also starting from a lower point. So if we take two of these examples together and put it side to side, on the left is a plot for the appendicocostalis, and on the right is the comparative muscle that next to the appendicocostalis. And we can see whatever muscle is, when the muscle is activated for the appendicocostalis, it has a higher mechanical advantage already. It has a greater moment arms compared to the muscle next to it. So it has easier time to rotate the rib towards inhalation. So this would come out as a mechanical inference that we can say, okay, the presence of uncinates can increase the mechanical advantage in the form of moment arms for appendicocostalis muscles. And it works better than the muscle with than individual without an uncinate. So basically, kind of like this. And the two curve is just representing whether you have accelerations or not. There's a slight difference. I can go on for days, but it is not really affecting our interpretations on the mechanical advantage. And I hope the last part is not too confusing. If it is, just ask questions and I can always clarify. So if I can sum up a little bit, that would be, we can use surface features on the uncinate scars or some of the microscopic features like the organization of Sharpie's fibers to identify the presence of uncinates, even if uncinates themselves are not preserved. So we have a method to consistently find uncinates in the fossil records. And our reconstruction so far suggests that uncinate is likely a feature in archosaurs in general, so they should all have uncinates. And then the last point is the little fuzzier point is the uncinate assist breathing by providing a greater moment arms for skeletal muscles, in this case, appendicocostalis in particular. And with that, I would like to acknowledge I'm giving this presentation from the Treaty 6 territory, and I would like to thank all my help from funding source, from my supervisor, Dr. Colin Sullivan, and all the collections allow me to dive into their collection and essentially play Peter Pan a little bit to find uncinates. And then also I need to thank all my wonderful colleagues and friends at the University of Alberta and the Athabasca Outreach for this wonderful opportunities. So if you have any questions and critiques, I'm more than happy to clarify and discuss more. Thank you.
Thank you so much, Yan-yin. I'm sure we'll have a number of questions. I just want to point out how you can ask your question. One is simply by unmuting yourself and just asking it straight out, and I would encourage you to do so if you want to do that. The other one is if you don't want to talk in public, you can click on chat and type it in the chat box. Before we go to the chat box, I would like to see if there are any audio questions first. and then we move to the chat box. And I see a hand raised. There's no reason, there's no need to raise your hand. Just go ahead and ask your question, please.
Hey, Yan-yin, you hear me?
Yes, go ahead, Koi.
Okay. Well, first, thanks for the talk. I think this is like the first time I hear you talk about your research. Just to clarify on your obsession with ribs in general. So for my questions, like on the histological level or like the tissue level, do you find any differences between the histology of Tyrannosaurid compared to like the extant archosaurs? You went over it a little bit earlier, but I think I missed like half of it.
Yeah, and it's kind of interesting. So I didn't go into too much details here, but oops, figure's too big. But you can see this layer of tissue. It's kind of like a mangled up osteons. So we haven't really figured out what is going on with this remodeling. We haven't seen anything like this in modern birds or crocodilians or even other fossil dinosaurs. This kind of mangled up piece is kind of interesting and confusing simultaneously. So this would be something I consider a little bit unique at this point. Another thing that also slightly unique would be structure over here. You can see in the bird sections, right? It's basically just enlargement of the central canal, so to make the osteon bigger and more hollow. But in the Tyrannosaurus slide, we can see it actually incorporates the surrounding osteon. It kind of digests all the osteon around it to make up this really large central canal, or it may not even be a central canal. It could simply be an empty space. So these two things would potentially be something unique, or at least characteristic of Tyrannosaurid on a histological level.
All right, thank you.
Thank you for your question, Koi. Yan-yin, when you talk, you could turn on your video if you wish, but you don't have to when you answer the questions. I'm sure there's a way to also share the screen simultaneously, but that's up to you. I'm just looking whether we have any other audio questions, and then we move to our chat. I hear nobody trying to ask a question, so let's move to our chat, and then at some point I have a question too. So the first question is by Jess Milling, and she says, I missed quite a bit of your explanation due to poor connection, so I don't know if you have covered this. What is the contrast of breathing of birds that are physically similar, but one has the uncinate process while the other doesn't? If it is related to breathing and arm movement, what are your thoughts of the role of uncinates in migratory versus non-migratory birds? So that's a big question.
Well, thank you for that question. Let me see. Thank you, Jasmine, for the really tough and wonderful questions. So I think for the first part is the contrast between birds with and without uncinate. So that would go to our moment arm plot over here. So I didn't use the name intercostal externi. I find that could be confusing for some people. So the intercostalis externi in this case is just a little bit next to the uncinates. So it represents a muscles or represents a bird without uncinate would be the situations like this on our right-hand side. And we can see it goes from a really low mechanical advantages, and then it gradually increases towards a point that is maximum, and then it reduces a little bit when the bird reach its max inhalation, basically. But if they have uncinates, then the muscle attached to the uncinates can start from a high mechanical advantage point and then continue to increase, and then like the counterpart is just decrease again back to a really low mechanical vantage point at max inhalation. It kind of, in my opinion, it kind of is more optimized pattern. So you're starting from high advantages, and then and later on you don't need as much as advantages half inhale. You kind of need to slow the ribs down so that we can stop the rib cage at max inhale, and that's why we have the reduction. We have the reduction of the momentum here, as opposed to the case without uncinates. Then you kind of still stuck with a decent size of mechanical advantage at max inhalation. So this one on the right-hand side is not as easy to start and not as easy to stop. And the one on the left-hand side with the uncinate is easy to start and somewhat easy to stop for the ribs. I hope that answers your first part. And so migration, I haven't checked on that area, unfortunately. There are some work done by Peter Tickle. He correlates the length of the uncinates. Let's see if I can find that figure. It correlates the length of the uncinate with the metabolism or the metabolic rates of the bird. I think he found positive correlations. So basically, the longer the uncinates or uncinate process, if you prefer, the longer the uncinate is, the higher the metabolism, the metabolic rates are. Sorry, but I'm not sure anything about migration or non-migration. I'm sorry.
Thank you, Chesme, for your question, and thanks for the explanation. Before we move down the chat, I have a quick question, because you mentioned at the beginning of the talk that there is the question of whether or not this is a homologous character. In other words, all archosaurs have inherited that from a common ancestor, and you've never really made your conclusion. Is that because it's not clear yet? It seems to me, based on your talk, that you would tend more to explain it as a homology. Is that correct?
We are leaning towards homologous structure based on our reconstruction, but maybe I'm a little bit too conservative in this way. So let's look at that ancestral state reconstruction in a bit. So we can see here there are thousands of species, and we only managed to find 36 species with uncinate scars or traces of uncinates. And even if I'm able to reconstruct it in a way that push uncinate back to Archosauria and say it is homologous, I'm a little bit skeptical with my results.
Fair enough. Thank you. I'm going down the chats, and there's a number of thank yous from Linda, from Morris, and from Evelyn about your talk, about how interesting it is. And then there's another question from Wang. Can one integrate under these curves or something similar to estimate the energy requirements of the variance for a cycle?
Yes, thank you, Wayne, for that question. That's exactly what we are working on. So it's not the energy that we are integrating. So to integrate that curve, what we are assuming is the muscle is contracting at peak contraction. So it's like we are exercising with a dumbbell. We are trying to do what they call isometric contraction, like holding the dumbbell in one position. So that represents the maximum force the muscle can produce. And the reason we are using this assumption is because muscle force produced by fibers are really difficult to evaluate if and then they really change a lot, and there's not a clear way to calculate it. But if we accept that assumption, and then we can cumulate or integrate all those curves, and then say those would be the maximum torque produced by all those muscles. And then we can sum up all those maximum torque for inspiratory muscle, or the breathing muscles, and breathe out or exhale muscles. Then we can compare the two values. If they are the same, then we can say, given our models, the muscles can reach equilibrium on their own, so they can work together without the help of any other muscles. If they do not equal, then we can say maybe some of the muscles are more robust than we expected. Then we cannot ignore the muscle contraction force, or there are some other muscles plays a role in breathing as well. So yes, that's a very interesting point, and I wish I have done more work that I can show you, but we are still working on our calculation at this moment.
Thanks. I've been looking for that for your next talk.
Thank you.
Thank you. So I'm just looking at the chat. Jasmine came back. She liked your explanations, but she has some sound problems, and she will review the video later. You gave us your email address in the chat for anybody who wants to follow up with you. So if you want to contact Yan-yin in the audience, look in the chat for the email address. And Linda, thanks everyone for joining. I don't see any more questions. Last chance to ask a question. Carmen liked the presentation, and she says it's very engaging. Thank you, Carmen. Any more questions or comments by audio or by chat? If not, then I want to thank you, Yan-yin, for an interesting presentation. Thanks for taking the time, and it was great. And I will hand this back to Linda now for some final words. Thank you.
Thank one that's left for joining in, and thank you, appreciate it. Hopefully others had a fine connection, other than the one person that was had mentioned that they had weren't able to hear the audio. So with that, I guess we'll close out tonight's presentation, and hopefully we'll see you guys at our next talk in February. Thank you. Have a good night.
Have a good evening.
Thank you, Yan-yin. Bye, everyone.